Okay, so I want to look over the 12 through 16 from your homework from yesterday. Hopefully the other ones were very similar to the ones that you did on the homework. Um, finding when does it stop? That's when does the derivative equal 0? When it's moving right, when it's moving left, kind of using the first derivative test, total distance versus displacement. And I hope you are checking your odd answers in the back. But 12 through 16 is kind of a good AP question here. And when they give you this picture and it says a particle moves along the x-axis, units are in centimeters. The initial position at t equals 0 seconds is 15. So that means they're giving us that ordered pair 0, 15. And it shows the graph of the velocity. The numbers are the areas of the enclosed region. And remember, that's what we're doing when we find the integral from a certain point to another point. We're finding the area under that curve. And so what they're doing in this is they're just giving you that. So there's not a lot to do here, but I do want to recommend that when you're doing these problems, besides just giving me the answer, show me what you're actually doing. Show me the calculus of it. And so that's why I wanted to go over this with you. So number 12 says, what is the particle's displacement between time equals 0 and time equals c? Displacement is just how far did it move. And so I think we could show that by saying the integral from 0 to c seconds of that function, of the velocity function. And it's important to show this, and as we get closer and closer to the AP test, a lot of times on the free response, they give you a point for just setting up the integral, even in this case where we don't have an equation. And so I really want to recommend that you start doing that, even if you didn't do it on your homework. The difference between your other homework and 12 through 16 is there's nothing to actually integrate here. You're using the picture. The integral is the area that's already down here. And from 0 to a is below the x-axis, so we already know that that's going to be -4. That's the area, it's negative. From a to b, that's above the x-axis, and they tell us that that area is 5. And then from b to c is below the x-axis, and they tell us that it's 24, but because it's below, it's -24. So I know without having an equation that the area or the displacement from 0 to c seconds is -28 plus 5, which would be an answer of -23. But I also want you to get in the habit of writing that as well. So that should help you on these other problems, but I'm going to kind of go through all these with you. Number 13 says, what is the total distance traveled by the particle in that same time period? And so again, this is what we talked about yesterday. Displacement is just what happened during that time. Total distance is the absolute value of that. So again, for number 13, I could write the integral from 0 to c of the absolute value of that integral, the velocity function. And that's what I would show for my work. And then again, absolute value means I'm going to take these same values from up here, but now I want them all to be positive. So it's like I'm taking the absolute value of -4 plus the absolute value of 5 plus the absolute value of -24. So you get an answer of 33. And again, on both of these, I could have put my units. It says the units are in centimeters. So both of these would be in centimeters. There's a question on one of the AP exams that has been released like this, where they give you that area. Number 14 says, give the particle's position at times A, B, and C. Again, this is like the ending position, which means we're going to have to use that initial value. I'm going to come up here and write number 14 here. So for A, what will be the integral that I would write to show what I'm finding from 0 to a, right? I'm kind of telling you the answer already. The integral from 0 to a of that function is going to be what's happening from 0 to a plus that initial position, so plus x of 0. And again, good practice to write it like that, but now we're just going to plug the values in. From 0 to a, that's just the area under that curve, which is -4, plus the initial value, which is 15, So that means the new position at a seconds is 11 centimeters. So that's at t equals a. And you should be able to go back and do B and C now, right? I'll kind of get you set up on part for t equals b seconds. We're going to go from 0 to b of the velocity function plus the initial value. And again, what's happening from 0 to b? Well, it goes -4, and then it goes up +5, plus, where did it start? At 15. So I think that ends up at 16 centimeters. And so I want you to do t equals c, since I did that part for you. So you're going to go from 0 to c seconds, plus that initial value. So remember the big difference between total distance and, displacement and the ending position. 15 and 16, it says approximately where does the particle achieve its greatest positive acceleration on the interval from 0 to b? So first thing to notice on number 15 is we're just looking right here from 0 to b. Think about, we're talking about acceleration, and so acceleration would be the derivative of the velocity function. It's kind of a hard question, I think, but probably looked at the back of the book on this one, and you saw that it said it happens at t equals a seconds. Think about the acceleration is going to equal 0 at the max and min of this. Like the acceleration would be here, and here would be a 0, because it's the derivative of this. So it's definitely not going to be at those middle points. And they really talk about like the steepness. Remember that acceleration is the derivative of velocity. So we're talking about where is that line the steepest and a positive number. And so the steepest part is this little section right here. It's a positive slope. And so they say it does happen at t equals a because it's steepest upward in that position. And then they ask the same question for the whole graph from A to C. So now you know what you're looking for. You're looking for the steepest upward part of that graph. It can't be anywhere here. And why is that true? Actually, all the way from here. It couldn't be here either. Because your graph is decreasing there, right? And decreasing would have a negative slope. And so you kind of have to compare which line is steeper. Is it steeper here? Or is it steeper through here? And if you look at those, I really do think that the second part is steeper, which means it is accelerating greater at that point. And so they say at about t equals c. And again, it's because the graph is the steepest at that point. Okay, and those are kind of harder questions, but 12, 13, 14, definitely things that you should be able to answer for me. So what we're going to do today is look at some more things. I wanted these notes to be printed out for you, so hopefully there's a copy here for you of these notes. And let's just get started. This I'm just kind of summarizing what we talked about yesterday again. We've been talking about integrals for a long time, and when you see the word derivative, you should think about rate of change, you should think about slope, but when you see integral, you should start thinking about that an integral represents the area under a curve. But not only does it equal area under a curve, we talked about yesterday that we can look at how far something has traveled, or total distance. And so again, I just wanted to reiterate those two differences there. If you take the integral of a velocity function, you're always going to get the displacement of that particle. And I know some of us struggle with what displacement actually means, but displacement is just how far the particle traveled. You can also use the integral of velocity to find the ending position, or the new position, because you have to factor in the initial position. And then anytime you see the word total distance or total area, you're not paying attention to sign anymore. You just want to know how far did it travel over that time, and that's always going to be the absolute value. And so this gives us total distance, which is the same as saying it's taking the total area under that curve, forgetting about the positive and the negative change there. So we're going to take that idea, and yesterday we spent a lot of time on equations. Today we're going to look at some graphs, and I took some of these from your book, and that's why I wanted to print these out for you. This is straight from your book. You're going to be doing, I think, number 17 or number 20, whichever one is like this. But they're giving you some graphs of a velocity function, and notice they're straight line graphs, or lines that can make geometric shapes, which means we don't have to know the function. We don't have to know the equation. And again, this is a big part of the AP test. It says the graph of the velocity function of a particle moving on the x-axis is given. The particle starts at x equals 2 when time equals 0. Again, notice this. This is a very important thing. This is our initial condition. And we have two parts. Part A is find where is the particle at the end of the trip. And part B is find the total distance traveled by the particle. Notice they never say the word integral. You have to know by reading that, oh yeah, that's what I'm going to take the integral of that function. So for part A, if I just want to find where it is at the end of the trip, I'm going to take the integral for the whole function, which on this one would be what? From 0 to 4, because that's where my graph stops, of that function. And is that it? Is that all I need to find my ending position? No, right? You have to add in, where did it start at x of 0? Again, just like the 12 through 16 from yesterday, I really want you to write that out. Show me what you're doing calculus-wise, and then use the graph. We don't have an equation here. We could write an equation since these are linear, but I want you to start thinking geometry here like we did back in chapter 6. I think I could draw a little line here down to the x-axis, and I could make this nice little 1 by 1 square for all of these. Is that going to be the area of each one of those? Well, it's kind of off a little bit. And maybe you notice what's going to happen here. The area of this would be a 1 by 1, but the area of this down here would be a 1 by -1, right? There's two rectangles above, like squares above the x-axis, and two below. So if I was going to write this, I'm going to put the two above together, and I'll say 2 times the length and the width, which is 1 by 1. But the ones below are going to be negative. There's two of those also, but they're going to be 1 by -1. So maybe you see what's going to happen there. The area is going to cancel each other out. You're just going to get a total area, a net area of 0 on that. But I have to add in where I started. My initial position was at x equals 2, t equals 0. So I'm actually adding 2 to that. So where am I after 4 seconds? I'm back exactly where I started because I went up and down and canceled each other out. What about part B? Part B says find the total distance. What do I got to do if I'm doing total distance? Absolute value, right? So again, show me. From 0 to 4, I'm going to do the absolute value of that function. Do I have to add in my initial condition if I'm finding total distance? No, I'm just looking what's happening from 0 to 4. So now this means I have 4 rectangles, and it's like they're all above the x-axis, right? So I'm just going to say, you could do absolute value, but I'm just going to say I have 4 rectangles, and they're all going to be a 1 by 1 if I'm not looking at signs, which means my total distance traveled is 4. I never had to have an equation to do that problem because of geometry. And I think some of those are the trickiest questions on the AP tests because we get so used to the equations, we forget that geometry is an option. Same thing with number 19 here. I'm going to kind of help you break this up, and then I want you to try it by yourself before I do it for you. But remember, you're drawing these areas into the x-axis. So I think you could have a nice little triangle here. Would be one area. You could break this up. Lots of people break it up into 2 triangles and a rectangle. But I'm going to break it up into a trapezoid. And after learning the trapezoid rule, we should know that. And then another little triangle here. So take a few minutes and see if you can set up those integrals for part A and part B, and we'll see if we agree. I'm going to go ahead and start. If we're still working, just pause the video for a few more minutes and then unpause when we're ready to go over this. If you're integrating this from 0 to 7, we want to break this up into these 3 parts that I've done here. And so this is the calculus part that I want you to write. Then underneath that, you should have some geometry to go with that. So here's my triangle. Triangle is 1/2 base times height. So I'm going to do 1/2. The base is 1. The height is below the x-axis, so I'm going to say my height is -2, so I get my sign right. Plus, this next one is that trapezoid, and remember trapezoid area is 1/2 times the height. How tall is that? 2. Times the sum of the bases, so that's 1, 2, 3, 4, plus the top is just from 2 to 3, so that's 1. If you broke that up into 2 triangles and a rectangle, you're still going to get the same area. Plus the area of this triangle, the height is just -1, I believe, so 1/2 times -1, but the base is 2. Kind of running out of room here, but plus my initial value, which was 2. So really the calculus part is just understanding what you're doing here, and then it's just some simple math here. 1/2 times -2 is going to be -1. 1/2 times 2 is 1. Times 5 is 5. 1/2 times 2 is 1 times -1 is -1. and then plus that initial value that we started at 2. So what is that? 7 minus 2, 5. Is my final answer there? Same thing for part B, find the total distance. Again, I can set that up by saying I'm going to take the integral from 0 to 7 of the absolute value of the velocity function, not taking into consideration that initial value. There's no need to redo this. We already did it down here, right? We just need to take the absolute value of each one of those. So it's going to be the absolute value of -1 plus the absolute value of 5 plus the absolute value of -1, which means my total distance traveled is 7. So don't forget, geometry is an option. Something else I want to show you is just some other uses of integrals. Story problems sometimes. It's just all about knowing when to do an integral. So again, this one is from your textbook. It says the rate at which your home consumes electricity is measured in kilowatts. If your home consumes electricity at a rate of 1 kilowatt for 1 hour, you will be charged for 1 kilowatt hour of electricity. Suppose that the average consumption rate for a certain home is modeled by this function. C of t equals 3.9 minus 2.4 sine of pi t over 12, where C of t is measured in kilowatts and t is measured in the number of hours past midnight. Find the average daily consumption for this home measured in kilowatt hours. So here's the big thing here. We want to know the average daily consumption, which means I don't want to know what's just happening at a certain time. Like if I said, what is happening at 3 o'clock in the morning, you could say, well, t is the number of hours that pass midnight, and if you plug in 3 for t, what's that going to give you? Yeah, it's just going to give you the number of kilowatt hours used for that specific hour. So at 3 in the morning, I could say that they use this many kilowatt hours. I want to know how much is happening the whole time, the whole day. And so another use of integrals is we like to call them the accumulator, because we can accumulate or add up things. It's kind of like thinking about the total area traveled, but not exactly. So if t is in hours, and I want the average daily consumption, how many hours are in a day? 24. So I can say the integral from 0 to 24 of this function is going to add up how much is used, not just for 3 in the morning or 4 in the morning or 5 in the morning, but for every hour in the day. So it's going to add all those up without me actually having to figure them. So it's a much faster way than actually saying how much was used at midnight, how much was used at 1 and 2 and 3 and 4. I can just integrate that and I can add all those up. And the great thing is, I'm not even writing that equation. I'm going to use my calculator, right? My best friend. NIT. So on my calculator, remember I'm just going to hit that button, and I'm going to type that equation in. And then I have to put comma t, comma 0, comma 24. And that's going to add that up for me without having to add it all up myself. And so what do you get? 93.6 kilowatt hours. And we'll do more of this as we go on and as we get closer to the AP test, but there's one on your homework today like this. I don't expect you to integrate that by hand. I expect that you just recognize you can integrate it and use your calculator. All right, I also have this other question I want to show you, and I want to kind of show you some extra cool tricks here. So I'm going to double page this. This is number 25 in your book, and it says, from 1995 to 2005, the Königsberg Bakery noticed a consistent increase in annual sales of its bagels. The annual sales in thousands of bagels are shown below. So 1995 to 2005, we have how many thousands of bagels are shown below. Now look at part A. It says, what was the total number of bagels sold for the 11 years? Hint, this is not a calculus question. So if those are the number of bagels sold from 1995 to 2005, what are you going to do to tell me how many were sold over that whole time? We're just going to add them up, right? And we can use our calculator. Just going to add up the sales. And we're just going to add this on our calculator, right? This whole column here. Just add it up. And I think when I did this, you can check my math here, I got 797.5. What does that mean? What are these in? Thousands? So maybe a better answer would be to put a comma in there. That's like 797,500 sales from 1995 to 2005. Now look at part B. Part B says, use a quadratic regression to model the annual bagel sales as a function of b of x, where x is the number of years after 1995. I want to show you this thing with your calculator that you can use. We're going to make a chart on our calculator. This is going to be our x. But notice it says x is the number of years after 1995. So what would 1995 be in terms of x? 0. Then 1996 would be 1 year after 1995, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And this is going to be our y-axis. And what we're going to do is we're going to kind of make a scatter plot on your graphing calculator. And then your calculator will give you the equation that matches that, the quadratic equation that then you can do some calculus with. So I just want to show you this. So use your calculators, get them out. And so just kind of be on that home page there. Trying to get my page right. Clear, clear, clear. Okay. The first thing you're going to do is you're going to go to your stat button. So stat is right down here below delete. And you should see this. And then we want to edit. We want to edit the statistics that we're putting in there. So edit's number 1. So you can either hit number 1 or you can hit enter. And you should get these lists. List 1, list 2. Oh look, mine are already in here from the last time I did this. But your list 1 is going to be your x-axis, and your list 2 is going to be your y-axis. And notice I just put in 1995, I put the year as 0, and I put how many thousand sales they had, which was 5. And I went all the way down. 1996 was 1, and I put 8.9. So take a couple minutes and put all those in. We're not putting anything in list 3 because we're only doing 2 variables. But you should end with number 10 which is 2005, they had 188,000. And kind of help each other if you need a little bit of help here. And this is really cool. This works with any set of data. If you have two things and you want to graph it and see what it looks like what shape it is, or if it has a positive or negative correlation, it makes a scatter plot for you. Okay, I'm going to go, but if we're not ready, pause the video. Everyone make sure they have their X and Y chart done. And then when you're done, unpause it so we can move on. So here's the other thing. We want to see what this graph looks like. So the next thing we need to do is we need to set our window. So I'm going to hit the window button. And I want to know what should my X and Y axis be. And if I go back here to my problem here, my X axis is just going from 0 to 10. So I think that would be a good window. My Y axis is going from 5 to 188. You can make it go from 5 to 188, but I just say pick some numbers that are included in there. So maybe, I don't know, maybe we can make our Y-axis go from 0 to 200, right? You want to make sure your values are in your window. Okay, sorry. Wrong button. Where's my calculator? Okay, so I'm going to go to my window, and I'm going to make my x-axis go from 0 to 10. My scale, I'm going to make it just go by 1. And then my y-axis, I'm going to make go from 0 to 200. And, I don't know, let's make it go, I don't want to go by 1s on my y-axis, maybe by 10s, maybe you can go by 50s. I'm just going to go by 10s, I think. And when I graph this, I got nothing, don't I? We got to turn our stat plot on. I forgot that step. So everyone make sure your window's good. Let's hit second y equals where it says stat plot. And all of mine are turned off because I didn't want these on, but we want to turn this one on. So I'm going to go over here to number 1, and I'm going to hit enter. And I want to turn it on. So notice now this is highlighted where it says on, it's flashing. You can make it make lots of things. I just keep this first one highlighted, which is like a scatter plot. You can make them any kind of dots that you want. Look, it says it's using L1 and L2, my list. If I hit graph again, I should see that I have a nice little graph. What kind of shape does that look like? Kind of looks like a parabola or part of a parabola, right? And so this is what a quadratic regression is. So here we go. To write the quadratic regression, we're going to hit stat again. Excuse me. But now we're going to hit calc because we wanted to calculate. And look at these different options that you have. There's a whole bunch of stuff that you have. But number 4 is a linear regression. If you ever graph some stuff and it looks like a linear equation, you can hit that and it'll give you the linear equation for it. This looks like a quadratic. So we're going to hit number 5. And I think if we hit enter, using our data that we put in, it tells you that it's giving you the a, the b, and the c for ax squared plus bx plus c. So what we've just found is an equation for our data down here is y equals 1.6x squared plus 2.3x plus 5. That's an equation that graphs that bagel company sales. So again, that was stat calc, number 5, enter. So let's go back, see what we have here. Part B, use the quadratic regression to model this in terms of b of x. So I'm going to say b of x is that equation that I just came up with, which is 1.6x squared plus 2.3x plus 5. And because we have an equation now, look what part C says. It says integrate b of x from the interval 0 to 11 to find the total bagel sales for the 11-year period. And you might say there's only 10 there, but year 1 was 0, so there really is 11. And so for part C, again, we could do this by hand, but there's no need to. I'm going to integrate from 0 to 11 of b of x. And I'm just going to use my calculator for that. And if I use my calculator, I got 904.017. Again, that's in thousands. So that's $904,017. Sorry, $904,017. And now look at part D. Part D says explain graphically why the answer in part A is smaller than the answer in part C. When we just added those up, we got 797,500. But when we actually took the integral, we got that was significantly more, 904,000. If you think about your graph here, when you just add them up, you're adding up that 5 amount, then you're adding up this amount, and then you're using this amount. Right, what we're kind of doing is we're approximating what's happening there. It's almost like we're doing a Riemann sum of that. And remember that Riemann sums do not give you an exact area. That's not a geometric shape. It's a curve. So to find the exact area, you do have to do the integral. And so you can look this up in the back of the book. I really don't want to write all this down. But A is smaller than C because C is the actual area under that curve, whereas A is really just a left Riemann sum, and left Riemann sums underestimate when the graph is increasing. So I wanted to show you that stat thing because I thought it was kind of cool. This is your homework. I don't think there's any on your homework that you have to do that stat stuff. I just wanted to show you it. But there are definitely ones on your homework where you can just use a calculator. I think actually number 26, you're using that same equation that we just found from part B. But it's really not that bad of a homework assignment. It's just kind of practicing doing this, okay? Get started.